So up next is Bartosz Gorecki from Queen's University of Belfast.
So hello everyone. Yeah, I'm Bartosz Gorecki, and I've realized here over the last 2 days that I may be the youngest person here, which is now incredibly daunting that I'm here presenting. But I've got an exciting project to talk about that I was fortunate enough to work on during my master's year last year, supervised by Charles Gillen, who was here a few years back actually, also presenting. So what I'm going to be looking at is neural networks and how we could possibly use them in the world of the intensive care unit, specifically for blood pressure prediction. So I'm hoping this works. So I thought I'd start off with an image, and what you're seeing here is what's an intensive care unit bed, but really it's an IoT environment of a very, very special kind. So all of these complex machines and sensors and wires, they collect masses and masses of data on a patient during their ICU stay, and this is then connected by an Ethernet cable, which is then connected to an electronic health record. And this electronic health record is considered to be big data, and that's simply because, as I mentioned, these sensors and complex machines are collecting this data at per minute intervals, sometimes even at 30-second intervals. So you're seeing quite a lot of data, and again, it's big data because of the volume, the complexity, the diversity, and the timeliness of the data. And then, obviously, the patient is in a critical state in this scenario, so the data that is being collected here is completely unique to any other healthcare setting because of this. And this then provides us with an opportunity to do some AI modeling to hopefully try and predict these parameters ahead of time, which can then help support patient recovery, as well as possibly discovering patient trends, which can lead to precision medicine, which really is the end goal with this. So in terms of what we're looking at specifically, it's blood pressure. Now, why blood pressure? Well, it's an incredibly important parameter in the ICU because obviously it brings oxygen to various organs in the body. It helps to measure blood flow, and it also, as I mentioned, it affects many organ systems. So for example, if the patient is under hypertension, which is high blood pressure, the people in the ICU need to act accordingly to administer medicine so that there's no adverse events such as organ failure or even death. And as you're seeing here on the right-hand side, I've put some graphs of systolic blood pressure on the top and diastolic blood pressure for one of the patients that we're looking at in this study. And you see really erratic and unpredictable blood pressure readings because of the critical state of the patient. So usually blood pressure, you see, the perfect region is 120/80, but in this scenario we're seeing a range of 160 to 90 for systolic blood pressure and 80 to 45 for diastolic, and this is over a 120-hour period. So you can see it fluctuates quite a lot for this patient. So what we're trying to do is basically make predictions in this dynamic situation where it's incredibly challenging because, as I mentioned, the critical state of the patient and also these erratic and volatile readings. How do we deal with those? So in terms of our approach, well, the challenge is to use multivariate data sets to predict blood pressure. So we have data, we obviously have systolic and diastolic blood pressure, and then we also look at things such as mean blood pressure, skin temperature, and heart rate, which are closely related. And we're trying to predict these 1 hour ahead. Now, whenever I say 1 hour ahead, what I actually mean is that we've averaged each data set into 50-minute bins, and I'll explain more on this later. And we're basically trying to predict 4 time steps ahead with these 15-minute bins, so it equals an hour. And we're trying to use patients that hopefully have a steady flow of medication during their stay, which again helps those volatile readings quite a bit. And how exactly we're going to be doing this? Well, we've used 2 models. We've used an encoder, decoder, long short-term memory network, or an LSTM, and we've also used a convolutional neural network, a CNN, for this. And again, the novelty of this work is the fact that we are in the ICU environment. As far as I'm aware, and I hope someone can correct me on this after, the only other university that works with ICU data, I believe, is UCL with their Chimera project. And also, again, the physiological state of the patient is another novelty here. In terms of where does HPC come in, you might be asking, well, as you all know, copious amounts of data and machine learning, it equals a substantial computational challenge, which is really what we've got at hand here. So in this study, we've used a UK Tier 2 HPC facility just across the water at Queen's University Belfast. It's known as Kelvin 2. So we've used it to grid search our models, and this is to hopefully optimize the neural networks so that they can predict as best as they can. So really the reason for this is because, well, really the long-term goal in terms of this work, and really is where HPC would come into practice a lot more, is the fact that we'd love to be able to continuously train a patient-specific model, which improves as more data is available, so it will be able to track the physiological and biochemical changes of the patient and hopefully make better predictions. So then HPC becomes a really, really key tool to be able to fit these AI models to data streams, to live data streams. And I've highlighted some of the specs there on the right-hand side for anyone interested in what we've got over at Queen's. In particular, for this study, we've used the CPU in bold there and also the Tesla V100s. In terms of the data and model preparation now, the data is really, really important to get right here before we can make any predictions. Again, as I mentioned, it's very unstable and erratic readings that we're seeing from blood pressure. And also I'd like to go into some more detail on exactly how we're doing the grid searching and also a bit more background on the models. So to start off with, I'd like to talk about how we're exactly preparing and pre-processing the data. So we've been able to collect a set of fully anonymous patient data sets from an ICU in Belfast, in the Belfast Trust. And as I mentioned, these blood pressure readings are recorded at 30-second intervals. So we've collected varying features for 5 different patients, and this includes, alongside systolic and diastolic blood pressure, we've looked at mean blood pressure, skin temperature, and heart rate. So in terms of then processing the data, we first have to remove the erroneous values that we're seeing and replace any missing values. So these usually come into play whenever there are sensor errors or sensor disconnection. And this can happen because, for example, the patient has had medicine administered, which causes sensor issues, or even they've moved in bed, which has caused a disconnection in the sensor, or they've been moved to a completely different bed, which then causes a time frame of no readings, which have to be accounted for. So in order to help this, we have used an approach where we replace these missing values with an average of the last 5 readings. So in terms of five last readings, that would be 2.5 minutes. So it's really just to get a clearer picture of where the patient is at that current time, to hopefully replace the missing values with a value that would be quite accurate of the current time. And then we have, as mentioned, averaged these data sets into 15-minute bins. So we've done this because there was a previous PhD student who worked with the same data set, but looking at tidal volume from ventilators in the ICU, and she used this methodology to predict tidal volume ahead of time. She found quite a lot of success in doing this, so I was recommended to use this methodology, which you'll see was quite successful. In terms of some further data context then, I thought I'd just put the slide up just to explain a bit more about the data. So we're using the 70-30 train test split for modeling, as we find that to be optimal. We've also scaled the data, as you see there, for training, because again, the nature of the blood pressure readings there, you saw, for example, systolic was 160 to 110 or 120 for one of the patients. So this will help the neural networks learn relationships a lot better when the data is scaled to a much smaller range. And I've put up some context behind each patient. So you can see we've got 5 patients, and we've got patient 1 with only 10 hours of data, while all the others have a couple of hundred hours. And I've highlighted patient 4 there because patient 4 is the one that we're using for this grid searching exercise, where we look for the optimal hyperparameters, and that's simply because they had the most data points. So now to show you what an actual average data set looks like. So on the left-hand side, and just a note, ABPS is basically systolic blood pressure, and you'll see this throughout, and ABPD is diastolic blood pressure. But what you see in blue is basically the raw data that's been recorded every 30 seconds, and I think this is over a 13-day period. And in red is the actual averaged 15-minute bins. So what this helps us to do is basically stabilize the data set. And as you can see, there was quite an erratic reading there that I think went up to 300, which I'm not sure is even possible, which may have been a sensor error. So it helps us to remove some of that more erroneous data and get a bit more of a stable data set to predict with. And in terms of the models that we're using then, we have, as mentioned, a long short-term memory network, which is a 2-layer encoder-decoder model. This is quite commonly used for natural language processing. But again, it was inspired by the work from the previous PhD student, Rachel, who had found success, again, in predicting tidal volume with this kind of model. We've also then used a CNN, which is a 3-layer, one-dimensional model. And I know this is very commonly used for extracting image features from raw pixel data. But again, we found quite a lot of success in using this model in this time series forecasting challenge. In terms of what we're doing then with the models, I thought I'd put in this bit of context at the end here, where we're continually, so basically we use the first 70% for the training, and then in the last 30% we do continual evaluation for the test set using walk-forward validation, which I'm sure you'll all be familiar with. But what we're basically trying to do is to mimic how we would deal with live data. So unfortunately, we've only been able to use historical data in this study. I mean, we would hope to use live data in the future. But as we're using historical data, we would have liked to mimic how that would look like when live data was fed in. So basically, we predict 4 time steps ahead. We then assess the actual versus predicted, and then we feed the model with the actual observed data for its next set of predictions. And in terms of the grid searching then, we've used grid searching for both models using Kelvin, the HPC cluster over at Queen's University Belfast. So first we did this on CPUs, and then we've done some work on a single NVIDIA Tesla V100 to see how it would compare. So I'm aware that grid searching is it's a brute force and very computationally expensive way of searching for hyperparameters. And if you can imagine, we've only done this for a single patient. If you imagine 32 patients at any given time in this Belfast ICU, it becomes an even greater challenge. So just to refresh, grid searching is basically a Cartesian product of all the hyperparameter sets. So in this instance, for the LSTM, we've used 1,024 hyperparameter sets. And for the CNN, we've experimented with 16,500. Now, this is actually shortened from even more hyperparameter sets that we had, but due to the time limit of the project, I had to cut it down quite a bit. So again, we've used patient 4 for these results. So in terms of the results, which is now the exciting bit of the presentation, where we can actually see how this has come to use. So there's a couple of things that I need to explain here, context-wise, in terms of this graph. First of all, we're using mean absolute error. Now, we also have recorded root mean square error, but mean absolute error is quite nice because it's less sensitive to outliers. And obviously, as you saw, it's quite hard to predict with the unpredictable readings. So mean absolute error was quite a nice score to show for this. The y-axis shows the mean absolute error. The x-axis actually has no physical meaning. It's really just an arbitrary number I've given to each of the hyperparameter sets, in this instance 1024, just to show a visualization of how the different models perform based on their hyperparameters. So I'm also only focusing on systolic blood pressure in this instance because we see the same sort of trend in diastolic as well. So one thing to note is obviously the GPU grid searching took 2.5 hours less, which is any time saved in the ICU is very important. But we're still looking at times of almost half a day, where in the ICU time is imperative, and we may not even have this amount of time to train a model before we can then apply it to a patient. So it's really important to get this right. So what we're seeing here from the actual results is you're seeing all the best scores clustered at the bottom, and they're within, I believe, 0.5 mean absolute error of our best configuration. So what this really tells us is that we've almost reached the limit in how well this model can perform, no matter what hyperparameters we throw at it. And it tells us that maybe the model is adapted as best as it can to the data that we have at hand. It also shows us that it's quite easy to find optimal hyperparameters for a patient. And it also shows us that maybe this approach is not the best. Obviously, the amount of time it takes is not ideal, but we could possibly, for a real-life application, look at setting a target score or even an acceptable error, which can then be achieved, so we can roll out the model to the specific patient. I've also got a slide on what it looks like for the CNN, and as you can see, it almost looks like a really rainy day where all the water's on the ground, but we're looking at 16,500 configurations here, and we're looking at over 2 days to find the optimal hyperparameter set, which is obviously not ideal, because 2.5 days in the ICU, the patient could be long gone by then, and it really makes no sense to be waiting that long for a model. So again, it poses the issue that obviously this grid searching exercise that we've done could obviously be greatly improved, and really the work that I'm talking about here is really the basis for any future work. So in terms of the actual data that we're looking at, I think it's quite blurry, but within a mean absolute error of 6 and 8 is where most of the parameters lie, is where most of the models lie in terms of performance. And again, it just shows us the same theme that we saw. We're able to find the optimal hyperparameters very easily, and maybe we're wasting a bit too much time on doing too many of these hyperparameter sets. So again, we're aware that this approach could be greatly improved for the future, and it's also imperative for this going forward, especially if we are looking at using HPC for continual model training for each patient, because as I mentioned, this is only looking at a single patient, not all 32 that could possibly be in an ICU at any given time. So in terms of the actual results of the neural networks, the CNN was actually the optimal model, although it's very close to the LSTM, as you can see there. So we're able to predict within 9% error for the CNN, while 10% for the LSTM. And I've given, again, the data context from one of the earlier slides, and I've shown the CNN results. So the thing to focus on there is whenever I say we're performing within 9% error, I mean 9% error of those ranges that you're seeing there at the end. So just to give a bit more context of how well it's performing. In terms of some further comments, again, I've shown root mean square error there, which is also beneficial in this study because it's harsher towards larger errors, so we're able to point out the larger errors, which are helpful then to improve our models in the future. In terms of the results, patient 5 achieved the best scores, as you can see at the bottom, and they also subsequently had the most amount of features, which could possibly tell us that for having extra features could improve our scores by quite a bit. And they didn't necessarily have the most data either, actually the second lowest amount of data points, as you can see. In terms of, I guess, almost I'm not sure how well that comes across on screen actually, but I was hoping this is going to be a money shot slide where I show the how well it adapts, but I'm not sure how well that comes across. But basically the bit down here, which is the last 30%, which is a test set for both systolic and diastolic blood pressure, you can see it adapts very well. So in red we're seeing the predicted, and I'm not sure how well that comes across. I had actually quite a bit of trouble getting the colors right on this, but blue is the actual data set, so you see the first 70% is the training data, and then the last 30% is the test data. So we've got in red the predictions there, and you can see it adapts very well to the blood pressure readings from that last 30%. And again, as mentioned, this is within a 9% error overall throughout the whole test set. Again, for context, we've used 82.5 hours for training, and we've used 35.5 hours for test data. And it's especially impressive because it was actually it actually performed quite well at adapting to that dip that you see here, where the patient's systolic blood pressure fell from, I think, 120 to 90 there over a period of possibly a couple of hours. So again, it's quite impressive, and I hope that this work can obviously carry on in the future as well. So in terms of some conclusions then, so we were able to use up to 5 parameters related to blood pressure per patient during their ICU stay. Kelvin 2, the HPC cluster, enabled our hyperparameter tuning, where we looked at thousands and thousands of configurations for our 2 models. We found that our optimum configuration was actually to predict both systolic and diastolic blood pressure was within a 9 and 10% error for both the CNN and LSTM. We've also seen that the CNN architecture could possibly be adopted in future for blood pressure prediction for all patients. And the scores that we've actually seen are actually quite broadly consistent with some of those reported in other papers that we've seen. And these include papers that aren't specifically looking at ICU blood pressure or ICU parameters either, so it makes the scores even more impressive. In terms of future work, I mean, ideally the list could be endless here, but just to point out a few things, the paper that I've written alongside Charles for this, it's currently under review, so hopefully that will be out there soon. Also, then we'd love to look at an improved grid searching process because, as you saw, it's still fairly inefficient. We'd like to be able to tune hyperparameters to each patient. As you saw, we've only looked at a single patient in this study, but we'd love to do it for all the patients because really that is the end goal that we're looking at, a patient-specific model that learns as time goes on and as during the patient stay. And again, as I mentioned, the continual model training and hyperparameter tuning from live data, as we were only able to work with historical data. And clinical trials, obviously, would be great. I think it's still quite far from that, but again, having this as a real-life application and being able to assess there would be great. And we've got lots of data. We've got 103 parameters for around 4,000 patients, and blood pressure is just a few of those parameters. So investigating those further could yield to even better results and hopefully even more insight for people in the ICU. In terms of some quick acknowledgements, I'd obviously like to thank Dr. Charles Gillen and Dr. Rachel Hagan, who were involved in this project both externally and internally. And obviously Rachel for the inspiration and the methodology, and also Dr. David Cutting for actually introducing me to HPC almost 2 years ago now, so I'd like to thank him for that. And also obviously all the folks that work over at Queen's University Belfast that manage Kelvin 2, because obviously some of this work couldn't have been possible without them. And I think that finishes me off. And I'd also like to thank all you guys for your attention, and Brian for having me here. And yeah, thank you.
Any questions for Bartosz? Yes, sir.
Thank you very much for your presentation. Can you please go to slide number 7?
Yes, slide number 7. Yes.
There you mentioned you recorded at 30-second intervals.
Yes.
And there were erroneous values and missing values as well.
Yes.
So what is the ratio of these kind of values that you need to replace or impute?
So a lot of the time what actually happens, as I mentioned, whenever a patient moves bed, the sensors are disconnected completely, so we just come up with lots of zero values. And because we're looking at time series forecasting, it's really important that we keep that flow of time series going. So being able to replace those values, for instance, sometimes there's sensor errors, so we see blood pressure in the minus, which is not really possible. And as you saw, we also saw, I think in this next slide here, you see that reading of 300 for both systolic and diastolic. Again, it's highly improbable, but it would be replacing values like that as well. So again, as I mentioned, the system that we've used for that is by taking an average of the last 5 readings for each of those parameters to hopefully help get a clearer picture of what could be going on at that time, even though there has been issues with the sensors or the devices that are recording the data.
Maybe you needed to add extra rows whenever there is complete missing rows for that 30-second interval.
Yeah. Yes.
And what is the rationale of this using these different number of features for different patients? Because actually 5 number of features is only for only one patient.
So in terms of the parameters, or sorry, the features you're saying? Yes, so it was really just what was available with that patient. So whenever a patient is in the ICU, not all of these parameters are always recorded, so it's really what we had available for those patients. So as I mentioned, the 5 that we used were systolic, diastolic, mean blood pressure, skin temperature, and heart rate. So I think the 3 in the middle there use a mixture of obviously systolic, diastolic, mean, and either skin temperature or heart rate. Patient 1 again was in the ICU for a very limited time, so they didn't record very many parameters for them.
Okay, one last question, maybe little bit beyond the scope of this work.
Yeah.
Did you ever try to test the modeling or the prediction based on the physician-informed some kind of activity, maybe for the imputation as well, or at least for the prediction?
So unfortunately, because of the limited time of the project, it was only a couple of months. And as I mentioned, the possibilities are endless for what we could have done. But that is definitely something that we could have looked at, yes.
Thank you very much.
Thank you.
Bartosz Gorecki, thank you.